All right, so next we're going to talk about vectors. Very important concept in physics and with just about any science that deals with motion or movement. So normally I play this funny little clip from Despicable Me about Vector and his introduction. If you would like to watch that, you can see the slides and check it out. It's funny. All right, so earlier we started talking about these things called scalars and vectors, but I didn't really tell you what they were. So now we're going to hear all about them. So a scalar is any physical quantity that has magnitude, which is size, but not direction. So it's just kind of a raw number with units, okay? It tells you maybe a distance or a speed, okay? But it doesn't really give you any indication or idea of direction. The power of a vector is that this quantity has magnitude and it has your units, but it also gives you a direction. So it doesn't just tell you how fast something is going, it tells you how fast and in what direction. So this is super important. And again, that's that difference between displacement and distance that we talked about before. Distance being a scalar and displacement being a vector. Okay, speed is a scalar, velocity is a vector, and velocity has magnitude and direction since it uses displacement. Speed uses distance, so it is a scalar. Okay. Typically, for notation, we represent vectors with a little arrow on top or with a bold letter. You might not always see this in my notation online because it's hard to denote that with my little tablet pen, but you'll often see this in text. So if you see a little V, for example, I'll try and draw it here. If you see, like, say a little V for velocity, and there's a little kind of like partial arrow above it, that means that it's a vector. If you see that it's very bold, that also usually means that it is a vector. I'm going to erase that for you. Okay, we can do math with vectors. So we have some different parts of vectors that we need to know about here. We have a resultant. So the resultant is the vector that represents the sum of two or more vectors. It's what you get when you add a couple vectors together. And we can use graphs to make better sense of this for now. So we're going to talk about some of the rules and pictures and images with resultants and vectors. Okay, so think of a resultant vector like the hypotenuse of a right-angled triangle, where the components that make up the vector are the adjacent and the opposite sides of the triangle. So you can see here we have our hypotenuse, and that would be our resultant. And then we have an opposite side and adjacent side. These two sides we call the components. Vectors have very special properties. They can be moved parallel to themselves in a diagram, which is handy. So you can kind of move them around however you would like. So let me draw an example of that. So if I have a vector here and a vector here, I can draw this one at the bottom up here, and that is okay. So we can draw them parallel to each other, which is cool. We can also arrange vectors tip to tail. Tip to tail is how we arrange our components. So components, vector components, get my pen back. Vector components are arranged tip to tail. So that means that when you draw a vector component, you need to draw, here's my vector. We need to make sure that the tail of my next vector is at the tip of this one. So the tip is the arrow part, the tail is the end. So my next vector would have to be like this. Okay, so always have to draw them tip to tail. Draw your components tip to tail. Your resultant, I'm going to pick another color here. Your resultant does not follow this rule. Okay, your resultant goes from, matches its tip to your first tip and matches its tail to your final, or its tip to your final tip and its tail to your first tail. Okay, So tip to tail is how we draw these things. We can add vectors in any order, which is kind of cool. So my resultant here you see in yellow, I could have drawn this in a different way. So I could have drawn this vector over here. Actually, yeah, I could have done that one over here, and then I would have to draw my other one right here, and I would still end up with my resultant going from here to here. I would still have the same exact resultant here. Okay? So you can draw them in any order you want, so long as they stay tip to tail, your components are tip to tail. Okay, to subtract a vector, we add its opposite. So if we were subtracting a vector, you would have to change the direction that you draw it in, and then you're going to get a different, oops, except I wouldn't want it there. I would want it tip to tail right here, and then you'll get a different resultant. Okay. Multiplying or dividing vectors by scalars still results in vectors. So if you end up having to multiply by a scalar, you will still have a vector. I'm going to go ahead and erase that. Okay, finally, let's remember that vectors have both a magnitude and a direction. Okay, you have to give a vector a direction in every problem. Typically, this would be a positive or a negative symbol, and often we have an angle above or below the horizon, or above or to the right or left of the vertical, or you might even have a cardinal direction like north, south, east, west, left, right, up, down. So we have to have some direction when we have a vector. And if there's an angle, you need to include the angle, and you got to find it. So naming these can get a little confusing if you get a little, if you get tripped up with the words. So I recommend that you draw and write stuff out to help you. Always draw and write to help you. So this first angle, describing it. This angle of this resultant, the resultant is the bold line. This angle is rising up from this dashed line. So this dashed line we're going to want to think of as a cardinal direction. And if we have a coordinate system here, we've got north, south, east, and west. So this angle is rising above the east. So we would say that this is theta degrees above east, or theta degrees north of east. So this one I would say north of east, or NOE. So it's starting from the east and it's rising toward the north. So sometimes it's helpful to draw that little angle indicator there. Okay, so let's look at the next one. And I'd encourage you to pause this and try these out before you listen to the answers. Pause it, give them a try, and then you can hear the answers here. Okay, this next one, we're starting from the north and we're going toward the west. So we would say that this is theta degrees west of north. Okay, so again, we're thinking about where it's going to. That'd be toward the west. And then it's coming from the north, so west of north. Now let's look at this one. Okay, so it's going toward the east. Okay, going toward the east, and it's coming from the south. This line is pointed toward the south. So this is going to be east of south. Now we'll look at the next one here. It's going toward the west and it's coming from the south. So it's west of south. Looking at number 5. We're measuring this toward the east. So east of. And this line, we can look at our vector. It's pointed north. So it's east of north. And finally, number 6, we're looking at this angle. It's going to be theta degrees, and it's pointed toward the north, so north of something, and this is headed toward the west, so it's going to be north of west. Okay, so again, what you're paying attention to is where these things are going and where the angle is rising up from. So if I had a problem that ended up with, say, number 6 was 32 degrees, okay, I would have to say it's 32 degrees north of west. Okay, so make sure that you are using all of your directions and cardinal directions, that you're aware of what those are before you tackle these problems. Okay, moving on. There we go. Stuff to remember. You should already know some of this from math class. The SOHCAHTOA might be new to you, so we'll go over it. So, Pythagorean theorem. A squared plus b squared equals c squared. Hopefully you all know that. What it's saying is that if you want to find the length of this resultant c, if you want to find the length of it, you have to do a squared, so one of your components squared, plus your other component squared, and then take the square root of it to get the other side. You should be able to rearrange this equation for any side that you want to find here. So if you're trying to find the resultant, square root here, get rid of that square there, okay? If you're wanting to try one of the other sides, you simply have to reverse that trend. You'd erase that so you can still see that equation. Okay, and then we have SOHCAHTOA here. So SOHCAHTOA is a really great way of memorizing these equations that help you find the angle or help you find one of the sides. So we use these if we have an angle and a side and a resultant, or if maybe we have both components and the angle. So we use these things to find angles or to find sides. So you're mostly going to be using SO and CA, but we'll use TOA a lot later as well. So SO stands for sine of theta is equal to the opposite side divided by the hypotenuse, or your resultant. Okay, and you can solve this for theta by taking the inverse sine. So say I'm looking for theta, say I'm looking for my angle. That's going to be the arc sine or the inverse sine on your calculator. So sine -1 of your op over your hype. Okay, and that's how you reverse all of these. So that's going to be important for you to keep in mind and for you to remember. And then Ka is your cosine of theta is equal to the adjacent side divided by the hypotenuse. And TOA is your tangent of theta is equal to the opposite side divided by the adjacent side. So SOHCAHTOA, write it down, remember it. You're going to be using it a lot, and they'll expect you to know it for an AP exam. And then also remember that by taking the inverse sine, cosine, or tangent of the side, that's going to give you the angle theta. Okay, so I would like you to practice these. Good idea to go ahead and practice some of these, but we'll go ahead and do maybe one or two together. So looking at number 1, we're going to numerically add the following vectors and find the resultants. When we're doing this, it's super important for you to draw a picture so that you can, number 1, see if you're solving it right, and number 2, see if your answer looks legitimate. See if your answer looks like it matches your picture. Okay, so we've got 15 meters east, and again, we can draw these in any order you want, but we'll start with this. We've got 15 meters east. So I would usually write 15 meters. And then we have 25 meters north. Typically, if you had graph paper and you all should because it's required for the class. I would expect that you draw these to scale. Try your best to draw them to scale. That would be required in some parts of the AP exam as well. So we've got 15 meters east and we have 25 meters north. And so our resultant, we can draw it, should look like this. And if you draw it on graph paper and you draw it to scale, you can actually measure your resultant if you know your scale, and you can measure your angle with a protractor, and you should be able to solve it that way. But most of the time, that takes a long time and it's tedious. So most of the time, we're going to be solving these numerically. Okay, so we want to find this resultant, this red-colored resultant here. So with this problem, all we need is the Pythagorean theorem. We have C equals square root of a squared plus b squared. So we can say that we usually measure our angle from the tail. So our adjacent side to the angle is this one. And our opposite side is this one, the app. Okay. And so we can go ahead and solve this. So 15 squared, and be careful of your order of operations, 15 squared plus 25 squared, and then we're going to take the square root of that. That gets us about 29 for our resultant. So C is 29 meters, but we need a direction. Okay, so this is just magnitude right here. 29 meters is just magnitude. We need to find direction. So that means we need to find this angle. Okay, so how do we do that? We can do that a couple different ways. We have two sides, and then we have the third, we have the resultant, but it's typically best to use values that don't have any rounding error. And our answer for this resultant, it's like 29.1547. It's some number that we had to round, okay? And so we don't really want to use that. So we're going to look at SOHCAHTOA. We have an opposite and an adjacent side. OA, TOA, we're going to use tangent. So we have theta equals the inverse tangent. TOA, opposite over hypotenuse, or over adjacent, sorry. TOA. And so we can go ahead and plug these numbers again. Remember, opposite is opposite the angle. So we'd have inverse tangent of 25 divided by 15. So if we do that, make sure your calculator's in degree mode. So we have inverse tangent of 25 divided by 15. And that gives us an angle of 59 degrees. Okay, now this is not how I want your answers to look. The official nice happy way of putting your answers in would be like this. So we have 29 meters, 59 degrees, and then we have to say 59 degrees from where? This angle is coming up toward the north from the east, so we'd say north of east. You could also say that this is north of the horizontal or above the horizontal. That is also acceptable in some problems. You could say 59 degrees above the horizontal, but this is what I'm looking for when I get an answer from you. Either that or above the horizontal. All right, so go ahead and erase that. Now we're looking at, let's see, we'll look at number 4. So number 4, we have something going east and then south, and then they go back west again. So our resultant is something like this. Okay, and that's kind of a funky looking thing. So when we have that, what we want to do is we want to look at every vector that is going in the same direction. So east, or is in the same plane rather. So east and west are in the same plane. They're both horizontal. So east and west are in the same plane. So what we want to do is we want to add them together. Okay, so 150 east plus 45 is going west. It's the opposite direction, so it's going to be negative, plus negative 45. Okay, so that's going to give us 105 east. So now we only have two vectors to work with. We have 105 east and we have 180 meters south. So we've got 105 east, we've got 180 south, and again, that's not to scale because I'm running out of room here. This is 105. And now we can draw a resultant, and we should be able to solve the problem just like we did the last one. Okay, so whenever you have multiple vectors, it's always good to break it down into one big triangle. Sometimes that means adding these things together in the way that we did. Other times it means doing several steps. Most of the time it means adding stuff together. So that's my example for you there. If you would like extra problem practice, and again, I have this on our Google Classroom website, you can go ahead and visit this page of your book. And these are the answers for the problems. Again, I give you the answers because I want you to have a chance to practice and try things out. This is not required homework, but if you would like more practice, you can give these a try. Okay, we already talked about distance versus displacement and speed versus velocity, so we will skip that. And we talked about rainbow dash. And this problem's kind of fun if you would like more practice. Distance travel, displacement at B and C. You can draw triangles between these spots and do SOHCAHTOA for extra practice. Okay. And there's another practice problem here, a couple other practice problems in here, if you would like to tackle them. Okay. Final note on non-right angle triangles. So say you're working with something that it's, not a SOHCAHTOA sort of situation. You've got this and maybe you have this. Okay, so these things are both at angles. What you need to do is these are essentially resultants, and you need to break them up into their components. So for this resultant, we would have a component here, and we would have one here. And for this resultant, we have a component here, and we would have one here. So we've broken it up into a few different components, and what we can do now is we can add all of those together. So we've got the component up here, we'll call this A, and this one B, this one C, and D. So we can add C and D together. That'll give us this nice long line. And we can add A and B together. Looks like it shortens A for us. So this is going to be A plus B, and this one's going to be C plus D. And that will give us two sides that we can then use to find our resultant here. Okay, so again, if we have some funky looking situation where you have these random lines that are at weird angles and don't have that nice right angle triangle that we like, you can make a right angle triangle, brute force it, and basically, again, all you're doing is you're breaking these lines into their individual components. Okay, you're finding their X and their Y, you're finding their horizontal and their vertical. Okay, so let me get that erased. I think that's all I have for you. This is some more practice if you want to do those trickier problems. I recommend doing at least one of these just to give it a try so that you're familiar with them. We won't always have those sort of problems, but it's good to just have that in your toolbox. Okay, so that's all I have for you. Hopefully that helps sort out some things for you before you go ahead and do that lab. Take care.